Hi guys, so today what we're going to do is we're going to go over capacitors. So we're going to try this capacitor question, but before we tackle the question, we're just going to go over some basic knowledge to make sure that we understand how capacitors work before we tackle the question. So what are capacitors? So capacitors, you'll see this electrical symbol. So capacitors, what we do is they've got two plates and we can charge them up using a cell. So normally we charge them up through a resistor so we can slow down the charging process, okay? So again, what we can do is we can charge them up through a resistor to slow down the charging process, because resistors, what they do is they obviously slow down that flow of electrons, that rate of flow of charge. But just so that we can understand them properly, we're just going to assume that there is no resistor. Okay, so we know the longer side on a cell is going to be positive and the shorter side is a negative. So as soon as we close the switch, so let's imagine we have a switch. As soon as we close the switch, what's going to happen is we're completing the circuit, so we're allowing electrons to flow around the circuit. So the negative side, what's going to happen is it's going to push electrons off that negative side of the cell. And those negative electrons are going to get pushed on to this plate, the plate on the right-hand side. So as electrons get pushed on to this plate, you can see that plate starts to become negatively charged. But we can see if I want to keep pushing more electrons, more negative electrons onto that plate, there's going to be a repulsion between the electrons already there. So it gets harder and harder to push more electrons onto that plate. So if I was looking at a charging graph to see how current was affected by time, clearly when we first close the switch, the current is going to be really high because we can push electrons onto that plate really easily. But over time, because it becomes harder and harder to push electrons onto the plate because of the repulsion of the electrons already there, that's why the current will drop over time and eventually get to zero when we can't push any more electrons onto the plate. And the time when it gets to zero, when we can't push any more electrons onto that plate, that's when the potential difference, so I put a voltmeter here, that's when the potential difference across my plates will be equal to the potential difference across my cell. So the other plate, what happens is the negative electrons get pushed off the plate and they're going to move around the circuit because they get attracted towards the positive side of that cell. So if something loses electrons, if we get rid of negative electrons, we become more positive. So that's how we get two plates with our charges then. One plate being negatively charged and one plate being positively charged. And that's why we were doing this practical. You have to be really careful that when you set up your capacitor, you always make sure that the negative side of the capacitor is connected to the negative side of the cell, because the negative electrons always get pushed on to that negative plate. Okay, so again, what we're saying is we're going to build up charges on these plates. And something in AQA, you might as well have a dielectric in the middle. And what a dielectric does, it just allows us to build more charge up into those plates. Okay, so here we can see our equations for capacitors that we use most often. And you see that current I is equal to I naught e to the minus t over RC. So what's that saying is the current at any time is equal to I naught, that's our initial currents, whatever this value is here, I naught. And it's exponential decay, that makes sense, it's negative. Negative time, whatever time we're looking at, over RC. So what RC stands for is the resistance times the capacitance. So that's why we said earlier that normally we charge up through a resistor because we want to slow down this process so we can actually graph it or take data points. So R is our resistance and C is our capacitance. And together you might see RC known as the time constant. And what the time constant is, it tells us normally about how long it takes for our capacitor to discharge. So now if we go to discharging. So we've charged our capacitor up, it's got the same potential difference across its plates as it does across the cell. So now if I take my capacitor and I'm going to connect it to a resistor, and there is my switch, what I want to do is I want to discharge. So this side is going to be discharging. So again, we've just charged it fully up to have the same potential difference as the cell. So this is my negative plate and this is my positive plate. And you can see what will happen is, as soon as I close that switch, I'm allowing those electrons to flow around the circuit. So my electrons get pushed off that negative plate and they'll flow around the circuit because it will be a complete circuit. And the electrons will keep flowing around the circuit until all of these negative charges leave that plate, and the plate will have a potential difference then across it of zero. So again, if we just look at it, at the start, we had that negative plate and our positive plate. So for discharging, if we look at current against time, when we first close that switch, so the switch was open, when we first close that switch, the current's going to be really high, right? It's really easy for those electrons to get pushed off that plate. So the current's going to be really high. But over time, as we start to lose that charge from that plate, the rate of current is going to drop. So as I start to lose those charge from that plate, the rate of the current drops to eventually it becomes zero when the potential difference across that plate is now zero, because there's going to be no built up charges on my plate anymore because it's being completely discharged through my resistor. So the other graphs we can look at is we can look at our charge and our potential difference. So for this graph, which again was us charging up our capacitor, if I was to look at a graph of charge against time, when we first had the switch open, there was no charges on our plates. So at the start, the charge was zero. And then when we closed our switch, we said that we're pushing electrons onto that plate, so the charge is going to be increasing over time. But because it gets harder to push electrons onto that plate, it's not going to be the same amount of growth. So that's why it's going to look like this curve. So the rate of charging is really high at the start, and then it starts to level off because it gets harder and harder to push more electrons onto that plate. If we look at how the potential difference across our plates changes with time, again, at the start, when our switch was open, so if we take all our charges off our plates and our switch is open, there is zero potential difference across the plates. There's no charges built up in the plates. So zero potential difference. As we close the switch and we start to build up those negative electrons onto our capacitor plate, you can see the potential difference will start to increase. But because it gets harder to push more electrons onto the plates because of that repulsive force, that's why, again, the potential difference will level off over time. If we look at for our discharging graphs, again, when we said that our switch was open and a capacitor, remember, has just been fully charged. If I look at my charge against time, we can see the charge in the plates is really high over time. And as we close the switch, the charge starts to decrease over time as my electrons flow around the circuit. So my charge decreases over time. If I look at the potential difference across my plates over time, again, when my switch was open, there was a really high potential difference between my two plates. But as I close my switch and those electrons start to get pushed off that negative plate, what happens, the potential difference will drop over time until it becomes zero. And that's when my capacitor is completely discharged. Okay, so this question shows us clearly, it shows about how the charge varies with time. The charge is increasing over time. So if the charge is increasing over time, clearly this is for a capacitor that is being charged. So this is a charging. So it says the graph shows the charging of a capacitor through a resistor. How long does it take to get to 0.3 millicoulombs? So I want to know how long in time it gets to get to 0.3 millicoulombs, so times 10 to negative 3. And I'm trying to figure out what time that takes. So clearly I have to look at my data sheet, I have to look at my formula sheet to look at how does charge vary with time when I'm charging the capacitor up. And that's when you see this equation. So what we're going to write down is Q equals Q naught e to the minus t over RC. So what it's telling us is charge at any time is equal to Q naught, the maximum charge. So to see what the maximum charge that can be stored in our plates, we look at our graph. And the maximum charge that can be stored in our plates is 0.6 millicoulombs. So that number there now is going to be 0.6 millicoulombs. E to the negative time, we're trying to figure out time. R, our resistance, we're told, and the capacitance, we're told. So R times C is just going to be 2,000 times by 4,700 microfarads. And the charge we're trying to get to is our 0.3 times 10 to the minus 3. So if we just fix this now to get rid of our milli, so millicoulombs is 0.6 times 10 to the negative 3, and microfarads, we know micro is times 10 to the power of negative 6. So if you get your calculator, what we're going to do now is I would probably simplify the bottom. So what we're going to do is 4,700 times 10 to the power of negative 6 multiplied by 2,000. And we get that number to come out as 9.4. So what I've got now is 0.3 times 10 to the negative 3. I'm going to divide both sides by this number to make it easier. 0.6 times 10 to the negative 3 is going to equal e to the minus t divided by 9.4. So now we're just going to do this end of the fraction. So what I'm going to do is 0.3 times 10 to the negative 3 divided by 0.6 times 10 to the power negative 3. And I'm going to get 0.5. So 0.5 is equal to e to the minus t over 9.4. Okay, the whole point is I want to figure out what t is. And that's why you have to remember your natural log rules. So the rules for natural logs is that I have ever got e to the power of negative x. If I take the natural log of that, it just becomes negative x. if I had e to the power of x over 2, and I take the natural log of that, it just becomes x over 2. So if you ever see an exponential raised to some power and you want to know that power, the way to get it easily is just take a natural log of it. So what I'm going to do now is going to take a natural log of both sides. So if I take the natural log of 0.5 equals natural log of e to the minus t over 9.4. We just said anytime you see the natural log of e to the power, it just becomes that power. So what I have now is our final answer is the natural log of 0.5 equals minus t over 9.4. So I haven't figured out what t is. All I have to do is take the natural log of 0.5, and then we're going to multiply by 9.4, and we're going to get what negative t is. So negative t in my calculator is equal to negative 6.52. So therefore, t in my calculator is going to be 6.52 seconds. So that's the time it takes for a capacitor to get to that charge. Just the last little bit to say there was about our time constant. So I said another nice thing to know about the time constant, we can use it when we're discharging. So if I look at my charge over time, the time constant tells us how long in time it takes that charge to drop by 1 over e. So if you type 1 over e in your calculator, it comes out as 0.37 or 37%. So the time constant is how much time it takes for this value to drop by 1 over e of its original value. It's just a quick way that you can also find out time constant. So, pardon me. Just remember to subscribe to get more videos like this and to hit the bell icon just to get notified about it.